All right, section 2.4, problem number 21. The directions are kind of wordy right here. We're supposed to determine points of discontinuity, state the type of discontinuity, and whether the function is left or right continuous, presumably at those points of discontinuity. So we got a lot to do right here. And number 21 is this weird function here, guys, that for some reason calculus and pre-calculus textbook authors love to throw at you here. It's sometimes called the floor function, sometimes called the greatest integer function. And it's written here with this little set of like L-shaped brackets around the x over 2. I've also seen it written in other textbooks as like a double absolute value sign. So if you ever see this notation right here, that would mean kind of the same thing here. So we cannot do this problem until we understand what that graph looks like. So let's play with this for just a second. And before I worry about this particular function, which is a variation on the normal floor graph, let me go ahead for just a second, and I'm going to keep this in a funky green right here. Let me graph here g of x is equal to, and I'm going to do the floor function now of just plain x. And then in a minute, I'll come back and I'll do the real one here of x over 2. So what this function means, everybody, it's not worth writing this down because it's not going to show up that much, but it means that we're supposed to take our input value, whatever x is, and we're supposed to return now, here we go, the greatest integer not greater than x, which was your input value. So I got to remind everybody, integers are whole numbers and their opposites, but no fractions, no decimals, no irrational numbers. So let's run through a few things. And notice I'm still in green, guys, so I wouldn't put this in your notes just yet. If we were to put a 0 into this function right here, the greatest integer not greater than 0 is 0. 0 is not greater than 0, so that one works. And if you put a 1 in there, the greatest integer not greater than 1 is 1. I think I see a pattern. The greatest integer not greater than 2 is 2, and the greatest integer not greater than 3 is 3. And let me go backwards here. The greatest integer not greater than -1 is -1. So right now, boy, this looks like just a linear function. It looks like y equals x. But this function is only interesting when you put in non-integer values. So if we were to put in something like 0.5, we're looking for then the greatest integer. And remember, 0.5 is not an integer. We're looking for the greatest integer not greater than 1/2. So 1/2 is between 0 and 1. Well, 1 is obviously greater than 1/2, so I don't want that. 0 is the greatest integer then that's not greater than 1/2. So when you put in a non-integer value like 0.5, it rounds this function down to 0. And that's going to happen right here at 0.5. Now, I didn't make a very big graph here. It would also happen at 0.2 and 0.6 and everywhere up until we get to this spot right over here, the 0.10, where we would have an open dot. And then once you actually get to 1, g of 1 would be the greatest integer not greater than 1, we said, then it jumps up to 1. So that's why this is sometimes called a step function. Everything between 1 and 2 rounds down to 1 until you have an open dot at 2, 1. Everything between 2 and 3 rounds down to 2 until you get an open dot there at the 0.32, and it'll do this, guys, so on and so forth, forever and ever. Amen. All right, and it'll keep doing that, and actually the same thing happens over here on the left as well. So that's what the floor function, I should say the parent graph of the floor function, looks like there in green. So now, let me go ahead and we'll switch to blue here. This is what we're actually going to play with. Let's go ahead and graph f of x. And I would love if you guys just remembered from all of the work that you did, probably most notably graphing trigonometric functions, variations on sine and cosine and tangent graphs, things like that, that anytime you take a parent function like this and divide your x by 2 inside the parentheses, or in this case inside that floor function, what you're really doing, guys, is extending the period of that function. Now, period isn't really the right word here because this function is not periodic. It doesn't just repeat itself over and over again like a sine wave or a cosine wave does, but it's kind of the same basic idea right here. So let's think about a couple of values. If we were going to do f of 0, that now becomes the greatest integer not greater than 0 divided by 2 is just 0, and the greatest integer not greater than 0 is 0. So this blue graph, this is the one you should be putting in your homework here, guys, starts at the same point. But what happens when we put in 1 now? Now we're going to take this 1 divided by 2, and now we're looking for the greatest integer not greater than 1/2. And it rounds that down to 0. So f of 1 is 0, and I got a closed dot right there. What about f of 2? Well, at that point, it's the greatest integer not greater than 2 over 2. 2 over 2, of course, is 1, and that stays put, and we get the point 2, 1. All right, and maybe you're starting to see what's going on here, guys. Any value we choose in between 0 and 2 is going to round down to 0 until we get an open dot right there at the point 2, 0. Then it jumps up to the point 2, 1. Then between 2 and 4, everything is going to round down to 1 until it jumps up here at that point. So this is effectively the same graph as the one we were just dealing with, everybody, except it's been stretched kind of twice as wide as it was before. So I think at this point, guys, you can go ahead and ignore pretty much everything I've got there in green. That was to help us just kind of figure out what the graph looked like. And now we can see the graph for this particular function here in blue. Y is equal to the floor function of x over 2. Now, by the way, not to ruin all the fun right here, your calculator will do this for you, guys. That function, I'm looking at it right now, is built into your calculator as something called int. So you could have gone to your calculator and typed in f1 of x is equal to, and if you just type in the letters int, and then put that x divided by 2 in parentheses, it'll graph this function for you. The only difference being your calculator won't show you those open and closed dots, which are kind of important to your conceptual understanding of this function right here, and something we're going to need to answer a question about one-sided continuity here in a minute, but the calculator won't do that for you. Okay, so now that we know what this function looks like, let me actually try to start answering some questions. It says first, determine the points of discontinuity. So let me they probably should have called this like A, B, and C, but here we go. For A, we can say that this function right here has, actually, let's go ahead and combine the first two questions. What types of discontinuity and where are they? So what we have here, everybody, is a spot, in fact, there's lots of them, one right here at 0, where the left and right hand limits don't agree with one another. And that is the very definition of a jump discontinuity. So f of x has a jump discontinuity at, and now here's what's going to happen. We've got this discontinuity here at 0, again at 2, okay, so 0 and at 2, and again one right out here at 4, and let's see, there'd be one over here at -2, and I think you can see the pattern here, guys. That jump discontinuity happens every 2 units. So what I would go ahead and say here is that jump discontinuity occurs at x equals, and since we're jumping by 2 every time, I would say 2n, with the understanding, this is kind of going back to something you guys did a lot in pre-calc, where n is any integer. Okay, a whole number or its opposite, but no fractions or no decimals. So for example, if n is 2, 2 times 2 would be 4. Yep, we have a jump discontinuity right there. If n were -1, 2 times -1 is -2. Yep, we have a jump discontinuity there as well. Okay, so that's the answer really to the first two questions, I guess. That f of x has jump discontinuities, and it has it all over the place at x is equal to 2n. And now they wanted to state is the function left or right continuous at those discontinuities right there. So f of x is, and let's talk about that. If we pick any one of them, maybe like this one right here at 2, the simple definition here is this, guys. This function does something to the left of 2 and something totally different to the right of 2. But which one of those two graphs has the solid dot? That would be this right-hand version of it right there. So we would simply say that f is right continuous at what? At x equals 2n, which again is any discontinuity that we came up with right there. So I think I've answered everything in that question right there. Hopefully that gives you guys some understanding of what that function looks like, but more importantly then, once you come up with the graph, how to answer these questions about discontinuities.